This video will demonstrate a Path Designer feature for automated desktop design of ring and spur networks. This is done in two parts. Part 1 is a fast walkthrough without explanation of settings, which will allow you to quickly see the process without being bogged down in detailed explanations. Part 2 is an explanation of the settings and how they affect the design result. Some examples will be demonstrated. The Path Designer main form is shown here. The tool has been loaded with a system of 55 sites with all possible links between them up to 3 miles in length. All paths are viable, meeting availability and clearance requirements. I'll now show you a map of this network in PathLoss. As you can see, this map is a mesh of links between all of the sites. All of these links are considered in finding a solution. Most will not be used in the final design, but some will become links in the rings and many may become spurs. In the main Path Designer form, the Network menu function Solve for Ring Networks is activated to start the process. This brings up the environment where the ring network design is performed. On the right is a simple map of the sites. This map will allow you to view the design progress graphically as we proceed. We start by clicking on Find Rings. The tool starts its search for rings, indicating its progress. For a large network, this can take quite a long time to find all rings, but the user can view the results as it proceeds by clicking on the Update Result button. The rings are then tabulated in the ring list shown here. These are numbered and the number of sites that make up the rings shown. In this example, a ring size of 11 sites is used, although a range of numbers of sites can be set. The geographical layout of rings can be seen in the map to the right by clicking on any individual ring in the list. Multiple rings can be displayed simultaneously. In addition, the sites that make up the selected rings are tabulated in the ring sites list here. Now this can proceed quite a long time depending upon how many sites and links there are. So I'm going to pause or actually halt the execution now. We have enough rings to show you some network examples using these rings. So it found 40 rings, and included in those 40 rings is a number of duplicates. So the final list that's tabulated in the rings list will be less than 40. If we scan down the list, we see we got to 34. So there was a number of duplicates that were removed from the list. We next click on Find Networks of Rings. The tool will then find network solutions using multiple rings and their spurs. The number of sites connected is also counted for each network solution. These are tabulated in the network's rings list, showing the number of sites, the number of common sites between the rings when there's more than one ring, as well as the ring numbers that make up the solution. So in the top one we have ring 1 and 14 that share a common site. Down below there's single rings because we didn't allow it to run long enough when creating the rings to get enough combinations. Now if I click on the top one, which has 2 rings, we can see the 2 rings graphically as well as their spurs. Once we have a good solution that we're happy with after running many combinations and verifying the solutions by clicking on the graphical list, we can apply the solution into Path Designer as a final solution. From there, all engineering, survey, and financial functionality is available to the solution. That's done by clicking on the Apply Selected Network as Final Solution. So now I'm going to talk about part 2, which is the setting details discussion. I'll bring up the editor form so we can go through the various settings. On the left is a list of sites in the network. Any selected site is used as a starting point for the ring searches. If you wish to have only 1 or 2 or 3 specific sites from which all rings connect, for example pop sites, only those should be selected when creating rings. If no sites are selected, as was the case when we ran our example a minute ago, if none of them are selected, the tool automatically selects all of them. So you can see they're all selected here. Ring parameters are set in this area at the top here. The user may set the range of the number of sites that make up a ring from minimum to maximum. Currently the minimum and maximum are set for 11 for this demonstration, but for our next run, which I'll do in a few minutes, I'll change it from 5 to 10 sites so we can see varying sizes of rings. There's also a smallest angle between paths setting. This is the internal angle inside of the ring. So if this was set to a very small number, you would get potentially you'd get a very pointed ring effect. For our next demonstration, we'll try setting this to 30 so we can see that in actual action. Network parameters are set in this area. In the ring area here, we start with the setting of disallowing or allowing overlaps of rings. As you can see in the example that's displayed, there are no overlaps. We can also set the maximum number of rings in a network. In this example, I set it for 5, although there's not enough sites or geographical coverage to get to 5, although I have seen 3 in this example, in this set of sites. We can also set the maximum number of sites that are shared between rings. So if I'd set this for 2, we might have a common link between 2 rings. So I will set for our next example to allow ring overlap. The next area is spurs. For the tool to include spurs, we have to check this checkbox. If we don't check it, then the tool will not figure out spur solutions as well. You can also set the number of links to a spur site. In my example, I used 1. As you can see, there's single links going to individual sites, but I could have set it to a higher number, and I guess I will set it probably to 2 for our next run. Lastly, you can set the number of spur sites that are allowed to connect to a ring. We have 55 sites total in this network, so for the next run I'll up the number to the full 55, although as many of those sites actually are on rings themselves, they will not end up as spurs, but this is a reasonable upper bound in order to include all sites. So with the changes that I've made, we can now click the Find Rings to rerun the network and see how it does. Now you can see we're finding a lot more rings very quickly, and that's because of the changes we made in the number of sites in a ring. So I'll just let it go for a second to get a large number, and then we'll see what we have. Actually, I can show you the update in the meantime, so we can just see a few examples. Okay, so I'm going to halt it and we'll take a look at what we have. So it's found 465 rings very rapidly, of which 354 were kept because the rest were duplicates. Now what's interesting is, and you can see for example in this ring that's shown here, first of all it's a smaller ring because I set the lower limit at 5 sites, and also you can see that the angle is very tight on this example. And there's another example here with a relatively tight angle. Some of them are not so tight, but you can see the effect of this angle as well as the number of sites in the ring. So now let's click on Find Networks of Rings, and remembering that we're going to allow overlap. We're also going to allow 2 links to a spur and to a spur site, and we're also going to have a large number of potential spur sites attached to a ring. So it's running, and I can do an update results now as it runs and see some results. Scan down to find an example with 2 rings. Here we are. Now you can see that the second link, there's 2 links to get to individual spur sites because of this 2 setting. Okay, so I'm going to halt it and we'll see if we can find an example of overlap. Give it a second to update the list. Okay, so I should also mention they've all been sorted by number of sites. So these solutions, each one of these is a solution, but the best ones come to the top of the list. If you scan down to the bottom, you see the numbers drop as it finds less solutions that have less coverage. So if I click on some of these, you can see the solutions come up. Now I'm not finding many overlaps because of the small rings that are being found. So I think what I will do is I'm going to rerun it. I'll put it back to say 10 sites in a ring. I'll put this back to 90, and I'll only do one link of a spur just to give another example, and we'll run it and we'll see if we can find some good overlaps. So we start again by finding some rings. I'll give it a few seconds here to find some. I'll pause the video for a minute to allow it some time to find a good set of solutions. Okay, so a minute has passed. We'll halt and see how we do for overlaps. Found 48 rings, including duplicates, which is actually 43. And I actually set it, as I said, to 10 sites in a ring. So there's a bigger chance of having a network solution with overlaps, which has been set as allowed in this setting here. So now I find my network of rings, and we'll just do some updates. It did them quickly, no overlaps there. Here's a good example actually of an overlap. So this is actually 3 rings, and one of them is here, and this one is over here, and you can see the overlap. So this is a situation where this parameter applies. Okay, so that's our discussion of part 2. There is one item that I do want to discuss briefly before the end of this presentation. I'll just bring that up now. So the last point here is the impact of possible directions. In other words, how dense is the mesh when you're building a ring, and in terms of the runtime speed and the number of possible solutions that you can get. So in this image, which is from a dense network, you can see that this ring that's in blue, in order to find this solution, what the tool did was, it's for this one site that it's starting on the left, which is S709, it made a choice out of, in this case, there's 19 directions it can go when it's searching for a ring. So it made a choice of this direction. When it got to this site, it had another 17 choices, so it made another choice there and continued around until eventually it found its way back. And this is a real ring that it actually found in a real network. Now, each of these sites that it goes through has many choices, so there's huge numbers of paths that can be searched through before it finds its way back to itself to create a ring. Now, I've tabulated the number of directions here for all the sites in this example, and you can see the first one's 19 directions, the second one has 17, and so on. When you start multiplying the number of possible choices that the tool makes as it looks for this one single simple ring, it turned out to be 38 trillion choices. In other words, there's 38 trillion ways to go through these sites. It's a massive number. So that means that when you have a very dense network, it can take a long time to find solutions as it searches. So that's a good motivator to keep the number of connections to a reasonable minimum while still achieving your design goals. Now for this network, we found 30 rings were found of 11 sites each, and this was done in 3.5 minutes, which is very good when you look at the density of the network here. So that's the end of my presentation. I hope it was interesting and informative. I thank you.